Okay, so in this video, we look at how the universal law of gravity can be used to determine this thing called escape velocity. Escape velocity is a term that we'd use to describe how fast an object would need to be moving in order to escape the gravitational pull from some body, such as maybe the Earth or the Sun. So it must acquire a certain amount of speed to actually get away from that gravitational pull. So we want to calculate that with this video. Maybe a simpler problem to solve first might help us understand how we're going to use conservation of energy and the universal law of gravity to determine that escape velocity. Let's consider this problem here. A box of empty film is allowed to fall from a rocket that's traveling currently at a speed of 1,800 meters per second from a height of 1,600 kilometers above the Earth's surface. We'd just like to determine the speed at which it would hit the Earth. We're going to ignore air resistance here. Might be suitable for this elevation, probably not as it gets closer to the Earth, but this should help us understand how to apply these principles. Let's first start by, I guess, drawing maybe an Earth on here, and I'm going to pull this little sphere in here, or circle, and let's just draw a quick little planetary rocket. So maybe an interstellar rocket here taking off and going off into the solar system, and it unfortunately drops a film canister. Both objects are moving initially at 1,800 meters per second. Well, the film canister now is going to no longer be acted on by those rockets, and it will go back out and then eventually back and fall into the Earth. And I want to know its impact speed. So how fast does it hit when it gets to the Earth? Well, to understand that, I'm going to try to use this little curve that we had drawn from before. And let's see if we can't do that. It's an energy curve. So energy is a function of position. And so if you remember from maybe a previous lesson, we use the surface of the Earth. Radius of the Earth is like right here, let's say. So we're at this distance already from the surface of the Earth. This is this curve would look something like this here. It's describing the potential energy due to a variable force using u of infinity to be 0. So if you're confused by that, make sure you look at that other video that was posted regarding that derivation for a potential energy function. We have this, we also have kinetic energy for this thing. So this thing has some initial velocity, so it also has kinetic energy. I'm going to draw that up here. So since this is an energy curve, the object can also have some kinetic energy. So let's say that it is presently at this particular spot along the potential energy curve, and it's got kinetic energy as well. Now, when the film canister comes out of that rocket, it's going to continue to rise up and travel this way along that potential energy curve. Well, as it rises, of course, it's going to lose kinetic energy. Now, the shape of that kinetic energy graph should mirror this. And so it's going to, any change in potential energy should be offset by changes in kinetic energy. And so that thing's going to go like this as well. And so again, these are supposed to be somewhat symmetrical, not right around the R axis here, but about some center line. And so it would be symmetric like so. Now certainly when it gets to this point, it will have stopped moving. That's where it's got 0 kinetic energy. If I let the red be kinetic energy, it will stop moving there. And so it will reach some maximum height, which would be right around there, and then it will of course reverse track. It will start coming back the other way. Well, the same thing will happen with its kinetic energy. It will be starting to ride this way on the curve. Once it gets back to the original spot, so right here, it will have reached the exact same speed that it had from before, but in contrast now, it will continue to fall back towards the surface of the Earth, eventually hitting, and as it does so, the kinetic energy will of course rise as well, and it will reach some final kinetic energy. Let's go ahead and label some of those things. Here's KE final. This is where it started. So this is KE initial. And if you consider what happened to its potential energy, this was U initial. So U initial. And this is U final, which would be U at the radius of the Earth. Okay? And so, again, the idea here, conservation of energy, says any changes in potential energy must be offset by changes in kinetic. Now, let's determine that speed using law of conservation of energy. Delta K plus delta U is equal to work non-conservative. And in this case, since gravity is a conservative force, those changes would essentially offset each other. 1/2 mv final squared, that would be the velocity and impact, minus 1/2 mv initial squared, the initial speed, plus, let's see, delta U, its final gravitational potential energy would be U at the surface of the Earth, and the initial gravitational potential energy would be U at the radius of the Earth plus 1,600 kilometers. And when I do that entire change, I get 0. Let's go ahead and clean this up just a little bit. We defined the gravitational potential energy as a negative g, m of the object, m of the Earth, all over, in this case, it would be the radius of the Earth, and then minus negative g, m of the object, m of the Earth, all over the radius of the Earth plus 1,600 k, equal to 0. And sure enough, we see that every term has an m in it, and so I could factor out that m. Then I have a product equal to 0. That means either m is equal to 0 or what's left is equal to 0. That allows us to effectively cancel that m out of that equation. And if I want to get an expression for v final, the velocity on impact, I'm just going to move everything over to the other side. And so let's see, this would be a plus over here, so it's going to be a negative. I'm going to take this one over first. So this would be g, m of the Earth, all over the radius of the Earth. Let's see, so that would be over on this side positive. This one is positive to begin with, so now it's negative on the other side. G, m of the Earth, all over the radius of the Earth, plus 1,600 kilometers. And then this was negative over here, so plus 1/2 v initial squared. And everything looks good. When I go through, plug in all those numbers, there's a lot of number crunching there, but the value that I get for that is about 5327 meters per second, or approximately 5,300 meters per second. So that would be the speed that it impacts the Earth using conservation of energy principles and the law of conservation, the law of universal gravity. Now, that's going to help us understand this thing called escape velocity. It's a very similar solution, except with a slight modification. There's an old saying in physics, what goes up must come down. And I'm going to add to that this extension, unless it's thrown very fast. So if we throw it fast enough, we should be able to escape Earth's gravitational pull, or any other body that is exerting some sort of gravitational attraction. So let's consider an object that is very far from the Earth. So its gravitational potential energy is essentially 0. So we're way out here, okay, perhaps way out here at this particular point. Now it's not moving, so it also has 0 kinetic energy at this point. If I were to give it just a slight nudge, what would happen is it would start to travel towards the Earth. Its potential energy would be riding along this curve until eventually it reaches its potential energy at the surface of the Earth. Well, because it started with very little or no kinetic energy, the symmetry line would essentially be the r-axis here. So it would be this thing here. This would be an exact mirror of this curve, except it would be up here, and it would strike at some point kinetic energy final, such that the total energy is equal to 0. I'd like to determine what that speed is. And so let's see if we can't go ahead and do that using conservation of energy principles. Delta K plus delta U is equal to the work non-conservative, which again is equal to 0. Its final kinetic energy, 1/2 mv final squared, started at rest, plus its change in potential energy. Well, its final is, let's go ahead and write it as U on the surface of the Earth. Its initial was essentially 0. Let's go ahead and replace some of these equations with other symbols. So mv final squared. This would be minus g, m of the object, m of the Earth, all over the radius of the Earth. Let's move that over to the other side. And sure enough, those things reduce out. V final would be the square root of 2g, mass of the Earth, all over the radius of the Earth. Let's go ahead and plug in some of those numbers here. So for this one, let's see, we got 2, 6.67 times 10 to the negative 11. Mass of the Earth, using kilograms there, 5.98 times 10 to the 24th. And the radius of the Earth, by the time it gets all the way back to here, it would be about 6.37 times 10 to the 6 meters from the center. And we would get for that speed something about 11,200-ish meters per second, or approximately 11.2 kilometers per second. This number is pretty important, the 11.2 kilometers per second. It happens to be what's called the escape velocity for any object. If it started at the surface of the Earth, it would have to be traveling that fast. It's essentially the same thing we just did, except in reverse. The idea here is if I have an object starting at the surface of the Earth, it would have to have this kinetic energy, such that when I fired it away, it would travel along this curve and go basically the opposite the way that it did before. And so that having just that amount of kinetic energy would be just enough to be able to get it out to a position where its potential energy would be zero. So it would take it as far away, or it could go wherever it wanted to and escape Earth's gravitational pull. That number is right here, actually. It's the 11.2 kilometers per second. And that tells us how fast an object would need to be moving if at the surface of the Earth in order to escape the pull of Earth's gravity. Now, this R sub E, this would be only if it's on the surface of the Earth. What if it were already at a position of 499 kilometers above the Earth's surface, so like the International Space Station? If I were to consider where the ISS is here, it would be maybe around here somewhere. So it's already at some elevated position from the surface of the Earth. What that means is that it wouldn't have to have as much kinetic energy in order for it to escape. So this radius of the Earth, when I come through and do this equation, V escape for the International Space Station would be 2 times G times the mass of the Earth, all divided by the radius of the Earth plus 499 kilometers. Now when you go through and do that solution, you would get a value that's closer to about, it looks like about 10,780-ish meters per second. That would be how fast the ISS would need to be traveling in order to escape the Earth's gravitational pull, simply because it's already elevated. Now let's see if I think I have some information. There we go. Here is the speed right now of the International Space Station as it orbits the Earth in a nearly circular orbit. It's about 7,667 meters per second. It's traveling about 4.76 miles per second. Its orbital height about 254 meters. If I wanted to escape the Earth's gravitational pull, if I were on that ISS, I might need to fire the rocket engines and get up to this speed. What that would do is that would allow me to eventually, this is the Earth, this is the current ISS moving through a circular orbit, increasing that speed would eventually allow it to then go off and escape Earth's gravitational pull. So there we go. A little bit of escape velocity using both the law of conservation of energy and universal law of gravity.